Greeting to respective lecturer of Integrated Design Project 1, Semester 2, Session 2021-2022. My name is Tan Diao. I'm from Group 5 and my major department is Earthwork. Today, I'm going to present Earthwork. I have been working with my teammate Cui Hong Bin, So Li Yuan, and Mohammad Imran bin Kamal. First of all, what is Earthwork? Earthwork can be defined as the basic principles that are included in all stages of project, from tiny tasks to huge buildings. It involves a large amount of soil for macro construction. Besides, earthwork comprises the modification of natural slopes to suit the requirements for transport systems like roads and the formation of canals for drainage for water discharge, which requires cutting and filling. There are four major activities of earthwork scope, which are site clearance, excavation of original surface, backfill the surface to the proposed level using excavated or imported material, and level of and compaction of excavated surface. First, site clearance is done before construction begins to allow for further remedial, treatment, or demolition work. It requires the removal of any machinery or equipment, unwanted excess materials, trash and other items from one location, removing vegetation and surface dirt from a site, leveling and preparing the ground for anticipated construction work are examples of site cleanup. It is important to double-check that all necessary approvals are in place, especially for trees that may be protected. Excavation of original surfaces is described as the use of tools, machinery, or explosives to remove soil, rock, or other material from open surfaces, holes, or cavities as part of construction or demolition work. Any earthwork, trenching, cofferdam, cohesion, shaft, tunnel, or underground work is considered excavation work. Removal of topsoil will remove vegetation, soil, and other decaying material that could make the land unsuitable for bearing structural loads. Cutting is the excavation or removal of soil from an area to obtain the desired proposed level. The filling process brings earth or excavated material into an area for the same purpose of achieving the desired level. Next activity is backfill the surface to the proposed level using the excavated or imported material. Backfilling is the act of reusing or refilling soil removed during excavation of foundations, subsoils, or other foundation works to support and strengthen structures. It serves as the base structure for floors, roads, sidewalks, and other infrastructures, as well as protecting foundations. Last but not least, level and compaction of excavated surface goes on. Grading is a construction technique that involves adjusting the slope and soil elevation around a construction site prior to construction. It involves laying or removing earth elements to ensure a level surface and a strong foundations. Successful grading projects require input from engineers. The main concept of the development is to create a business district with a range of infrastructure and facilities available to potential workers, as well as industrial spaces for various light and heavy industries. It will be developed into a multi-industrial area strategically located in Ulu Tiram, Johor Bahru. The actual location of the project area is shown below. The project will last about 5 years. The proposed industrial zone development will occupy one of the 443,554.23 m² project areas. The site inventory is used to identify all resources and environmental conditions that may be affected by the proposed development. Proper site inventory techniques can help engineers better understand the project site and environment, and often yield ideal site solutions. The proposed sewage treatment plant (STP) is located near main entrance 1. Retention ponds are located near main entrance 1 and main entrance 3. Roadside drains are located next to the retention pond near main entrance 1 and main entrance 3. At Zone 1, the proposed levels are highest at the top and lowest at the bottom. Sewage will flow into the retention pond and the drain stream will be discharged to the roadside drain located near main entrance 1. At Zone 2, the proposed levels are almost the same and the altitude is stable. Sewage will flow to the retention pond and the drain stream will be discharged to the roadside drain located near main entrance 3. At zone 3, the elevation rises from left to right. Sewage will flow to the retention pond and the drain stream will be discharged to the roadside drain located near main entrance 3. This slide shows the existing road level and existing roadside drain and culvert. Besides, the type of industry and facilities are shown in the table below. For Industry Ringan Cluster, there are a total of 156 buildings. Industry Perkhidmatan Cluster have 8 buildings. Industry Ringan Reservoir have 20 buildings. Industry Ringan Berkembang have 44 buildings. Industry Perkhidmatan Terrace have 90 buildings. There are 1 Asrama Pekerja, PPU, Tangki Air, PE for SC and Logi Rawatan Air. There are 14 PE for DC and 2 kolam tadahan. As for total, the proposed project site have 339 buildings. The proposed level in this project were designed using a trial and error process until the optimal proposed level was found. When designing proposed level, some features such as existing road level and project area topography must be considered. Some of the information required early in the design includes existing drainage flows, existing road levels, contour lines, project area boundaries, and natural drainage levels. When engineers consider the design and construction of a building, they must first examine the existing condition on the site. Cut and fill are used to determine the amount of land to be added or removed. However, the percentage difference between cut and fill for any given project should be less than 15%. A cut is created when the soil is removed from the intended ground level, and filling occurs when soil is borrowed to fill a hole to the desired ground level. To create a flat ground, cutting and filling is a standard method. Land cutting and filling entails certain risks, especially when land is landfill. We use Autodesk Civil 3D software to calculate cut and fill volumes. One surface for the original ground plan and another for the proposed ground plan were created in Autodesk Civil 3D. Then, the volume of cut and fill is calculated by comparing the surface. TIN and grid models in Autodesk Civil 3D are used to analyze cut and fill volumes. Triangular irregular network TIN models fits a ground or other irregular surface using a series of connected triangles. This irregular surface is composed of a series of consecutive triangles, each of which is generated from a series of irregular data points. In the process of constructing a TIN network, the TIN network is usually constructed with nodes, edges, and faces as their basic units, which are then represented by planes, resulting in a continuous representation of the terrain surface. In order to reproduce the real terrain, the TIN model can dynamically change the stored terrain data according to terrain fluctuations and perform appropriate processing on the terrain characteristic curves. When constructing a TIN network, the establishment of each triangle must follow 3 principles. First, each triangle must be as close as possible to an equilateral triangle. Secondly, the 3 vertices forming the triangle must be closest, and the triangle network must be unique. Hence, the TIN network be as close as possible to the actual terrain surface. The procedure to construct TIN model are as follows. First, select a data point A near the geometric center point of the area containing all the original data points. Then find the data point B closest to point A and connect A and B to form an initial baseline. Then use the empty circumscribed circle criterion to find the data point C that satisfies the condition as the third point. The 3 points A, B, and C form the initial triangle. Take the 3 sides of the initial triangle as the starting sides and use the empty outer criterion again to continue to find the next data point that meets the requirements. With this, we have found 3 other data points that fit our requirements. It should be noted in this process that the same site can only be used at most twice, otherwise the new triangle generated will be invalid. Repeat the steps of the second step until all the baselines are processed to form a complete triangle network. So far, the establishment of the TIN network has been completed. The grid method allows engineers to estimate the amount of cut and fill for an earthwork project by rationalizing the site into cells. The cut and fill can be calculated for each cell individually, and then each fill cells and each cut cell can be added together to get the total cut and fill. The grid method involves drawing a uniform grid on the earthwork plans and cancelling existing and proposed ground levels at each node of the grid. Use these values to calculate the average cut and fill depth required for each cell in the grid. And the volume of each cell is obtained by multiplying the depth by the cell area. The software estimates the depth of cut and fill at each spot where the grid line is by adding or subtracting the elevations. Based on the results, the percentage difference between cut and fill volume for TIM method and grid method are 7.01% and 8.39% respectively. Since both methods give a percentage difference of less than 15%, the proposed level is acceptable. Then we proceed to drawing of section view. This slide shows the view for longitudinal section. This slide shows the view for cross-section 1, and this shows the view for cross-section 2. Slope stability ensures safety by preventing slope collapse on construction sites. Slope failure occurs when a slope suddenly collapses due to a diminution in the Earth's self-sustaining ability due to rainfall or an earthquake. Natural slopes and man-made slopes are the two most common forms of slopes. Slope analysis is required during construction. Slope failure can take many forms. For rocky slopes such as fields and toppers, as well as sandy or clay slopes, slides and flows. Since levels and surrounding areas are expected to vary, soil will need to be cut and filled to create a stable slope connecting the two. Slope stability is very important as it can lead to erosion, landslides, and even death. For this project, we use the Bishop technique to determine the minimum safety factor to meet safety requirements. Slope stability is governed by two forces which are driving and resisting forces. The shear stress equation is shown below. As for our project, we use simplified Bishop method calculation. The equation to determine the factor of safety is shown below. The procedures to calculate the factor of safety using simplified Bishop method are shown below. First, draw the appropriate slope in AutoCAD for slope stability analysis. Secondly, the radius of the circular failure surface is randomly assumed. Next, make 10 identical cuts from filling soil mass. After that, draw a straight line from the center of the circle to the middle of each slice. Next, the angle formed by the two lines is written as alpha. Since no drilling data were provided, soil parameters were assumed. To calculate the factor of safety value, use a Microsoft Excel worksheet. For our project, the black circles represent the slopes to be studied in the figure. These are called critical slopes because the height difference between the two ends is usually the largest in the entire slope area. The critical slope is defined as the maximum angle between the slope and the flat ground, and the height difference between the two ends is quite large. Since critical slopes have the greatest risk of failure along the failure surface, if these three slopes can prove to be stable with a safety factor greater than 2.0, the other slopes around them will also be stable. For slope 1, the slope ratio is 1 to 2 and the height difference is 7 meter from 55 meter to 48 meter. The soil parameters are shown below. As for slope 1, the inputs such as height Z, width B, and angle alpha are recorded in the table. The factor of safety obtained is 2.12, which is higher than 2, considered as acceptable range for slope stability. For slope 2, the slope ratio is 1 to 2 and the height difference is 10 meter from 44 meter to 34 meter. The soil parameters are shown below. The factor of safety obtained for slope 2 is 2.87, which is higher than 2, is considered as acceptable range for slope stability. For slope 3, the slope ratio is 1 to 2 and the height difference is 9 meter from 70 meter to 61 meter. The soil parameters are shown below. The factor of safety obtained for slope 3 is 2.45, which is higher than 2, is considered as acceptable range for slope stability. All three of the chosen slopes have a factor of safety greater than 2. Hence, without additional reinforcement, the slope stability is enough. However, to prevent soil erosion and sedimentation, it is necessary to grow rooted plants, such as grass planting in order to maintain soil grip. That's all for me. Thank you.